I was explaining the perceptron and early development in AI in my class the other day, and a student asked an astute question. Why are we looking at this 2D graph of a decision boundary of a perceptron? Well, it turns out that machine learning is really critical to AI and to understanding what's going on, so I wanted to dive in that here in this video. If you look at artificial intelligence, a large part of it is comprised of different machine learning techniques. If you break that down, the key technology, in my opinion, would be neural networks. And you can see this quote from Sam Altman here. He just released a blog where, how did we get to this point? He's saying that deep learning is the key. It actually works. So deep learning is large neural networks with many hidden layers, able to learn very sophisticated patterns from looking at probabilities and the statistics of data from the real world. So within deep learning, you get all these capabilities, generative AI like ChatGPT, but also you can make predictions, you can make recommendations. How does Netflix, for example, decide what movies to show or to highlight or preview that it thinks you're going to want to watch? It's using deep learning. Now, what can we do with that? So I think we can all agree that for something to be intelligent, we are talking about AI, it involves making decisions. So decision making, you take knowledge that you've already learned, that could be from learning lessons the hard way, you read about a topic, whatever that might be, and then you take the information you know about a given situation. Those two things combined, you can make a decision and then take some action based on that. So do I need to study more for an upcoming exam? Well, how many, or rather, what would you consider? How much have I studied already? How many hours? Did I attend all the classes? Did I hear the lectures? Is the material fresh in my mind? And how much sleep am I getting? Maybe I just need to get more rest, and I'd be better served by going to bed early and just being fresh when I take the exam tomorrow. Now, let's say we wanted to codify that decision. If we were going to write a classical program for this, we would have to decide on what are the explicit rules. We would say, well, if the hours of sleep we got is sufficient, then I can consider studying more. Okay, how much have I already studied? You would have a very complex spaghetti-like code trying to figure out. It wouldn't be very flexible. Machine learning, what you can do is take a lot of data. So we're going to look at, in this video, some data set from Kaggle, where we have a bunch of data on different students and their characteristics and how they scored on an exam. Machine learning, we're going to back into what the solution is by just observing the real world and coming up with a model that we can use to predict that. So this is our data set. It has student performance factors, and I've just taken a look at the head of the data frame that I loaded it into pandas. You can see here there's 19 columns. The first couple are pretty important, the hours studied and the attendance, so what percentage of class did I go to? But then there's lots of other data as well, including do I have access to internet? Am I involved in extracurricular activities? Lots of good stuff. Okay, so what am I going to do with all of that data? Well, I can put it into a neural network. So the input layer is going to take all of those values, and the network itself, through these hidden layers, is going to try to learn what the pattern is, if there exists one, in the data. Now, this diagram is showing 4 outputs. We're just going to have a single output, which is we're going to try to predict our score. And then we can look at, based on the predicted score that we're going to get on the exam, we can make a decision. Well, should I study more? If I think I'm going to get a 70% or get a C, probably want to study some more. Maybe I'm happy if I'm in the 80s, or certainly if I'm in the A range. Maybe then it's just time to go play some video games. Okay, but what is happening in each of those neurons? So this diagram in the upper right is showing a single neuron. It's taking each of those data points that's coming in as input. Now in the first layer, this is the information from our data set. So I'm showing a couple of features here, is what we call the inputs. So in this first case, the number of hours studied is 23, attended 84% of the classes. Now here's an interesting bit. So computers, especially neural networks, only understand numbers. Some of our data is actually categorized. So the motivation level comes in as either low, medium, or high. So we need to translate that into a number, and you can see here the scale that we've used is 0, 1, or 2. Now in the neuron, each of those get fed in, and there are weights associated with each one. So how important is each of these factors? We add up all those values and then send it through an activation function to decide how much of a signal do we send to the next layer, or to the output. So this happens layer over layer. And we can think of these initial inputs, all of these numbers, as a vector. A vector is just a series of numbers. I've represented it here as the bracket with the three values inside of the bracket. So that's our first, and that's going to be transformed, that vector, at each layer of the network until we eventually get to an output, which is our predicted exam score. So you can think of, again, this input domain as a vector space. So what is a vector space? This is a really key concept. It's important to try to get a mental model of this. It'll really help you understand what's going on. So let's say we're just going to use one input value. We're just going to use the number of hours that you've studied. And that might be a reasonable thing to do. So in this case, it's 23. You can just think of that as a point on a number line. And maybe our decision boundary is just this blue line here. If we've gotten more than that, which looks like it's about 18 hours of study in, we're probably good to go. If we're under that, then we need to study some more. Okay, now let's consider using two of our input features. Let's use both the number of hours that we've studied and our attendance in class. So this is a graph that I created by asking ChatGPT to write some Python code for me and to figure out this decision boundary. This is actually using the perceptron. We're trying to see if we can have a linear separation between the categories of pass-fail, pass being a score of 60 or higher. So all of the red dots on this graph are students that have passed the exam. The blue dots are the ones that have failed. You can see there's a sort of a bit of a cluster in the lower left corner. So those would be students who haven't studied very much, and also their attendance is not stellar. They've missed maybe a third of the classes or so. But looking at this diagram, it's easy to see that you can't just draw a straight line. There's got to be more to it. So the other parameters or the other features that are involved also play a role. On the right side here, you can see I'm trying to show that our input vector, in this case, are just two values. So 23 and 0.84. So you can think of that as a vector on this graph. It's a 2D point and an XY coordinate. And all right, now we go up to three input values, and it gets a little more difficult to visualize because our brain starts to have trouble when we visualize in three dimensions. I think we can handle. Certainly at four, now it's becoming tough. But let's say in addition to study hours, attendance, we add the motivation level. Remember that we've had to convert the low, medium, high into a number. So in this case, it's medium, which is 1. And in the lower left corner, you can see what that 3D vector looks like. Now, one thing you'll notice is that it's pretty low to the surface because look at the scale of our values. So 23 is on a much bigger scale than these other values, which are a percentage. So that's going to be from 0 to 1. And then our motivation level, which is 0, 1, or 2. So for this reason, that having that much of a disparity in the values can make the models make it more difficult to learn the patterns. So often what happens is you scale those values. And you can see here, I've simply asked ChatGPT, well, how do I normalize this vector? And it's showing me the formula. That's probably going to look familiar because that looks like a variation of the Pythagorean theorem in 3 dimensions. So after I take the normalization of that, you can see on this bottom right corner, that red arrow. Okay, now I've got a little bit more reasonable vector to deal with, and I can more easily compare those features against each other. Okay, so what happens now when I plot all this? So again, we're in 3 dimensions, so it's getting a little more difficult to visualize, but we still can do it. So here you can see the blue dots are still clustered on the left side of our 3D vector space. But you can see motivation level, it looks like didn't really help us delineate very much. There's still some variation. So I don't know if that feature is going to really help us a whole lot. So what we'll do next at this point is take all of our features and put those into a neural network. And here is the structure of the network that we're going to build. You can see on the upper right corner, our input layer has 19 values. And so I'm showing you on the left, just the head of that data file. You can see the different columns, and there are 19 different values. This is the original source data, so it still has the categorized low, medium, high. So we are going to need to convert that like we saw earlier. And then it's going to go through a number of hidden layers. The first actually has 128 nodes, and from there it's common to kind of go down in size. So it goes 128, 64, 32, all the way to the output of the fourth layer, or dense 4. It's actually the 5th layer. And that output is just one single node, and that's going to give us the predicted score. This is a Google Colab notebook where I've done the analysis for this video. I'm just mounting Google Drive, which is kind of nice. You can access your data files there, and then importing that CSV using the pandas library. Printing the head of that shows you the high level, or the first few rows, the information. You get a sense of what data's in that data set. Here is where we convert our categorical values using the sklearn label encoder. So motivation level was low, medium, high. We need to encode that as a numerical value. Okay, now we're going to get into the actual neural network. We're using the Keras library, TensorFlow. And so here we're first going to take our pandas data frame and just select all of the numeric columns. Again, we have the additional columns, or the initial columns, as categorical data. We're converting those to numbers, but in terms of using them as inputs, we only want the numbers. We only want those columns. X is what you usually refer to as your input, so we're going to take all the data but drop the exam score, because that is what we're actually trying to predict. As you can see here, Y is our output, so that is just the exam score. And then this train test split function, what that does is it takes our data, and you can see the test size is 0.2, so 20%. So it takes randomly 80% of the input. It's going to use that as a training data set, and then the remaining 20% we're going to use to evaluate and see how did we do. So we start out, I mentioned that you need, or rather it helps to scale the values. So the standard scaler there is going to take all of our data, scale it, and then finally we get on the bottom our actual network definition. So we start out with our inputs, taking in our X training data. Our first hidden layer has 128 neurons, and then we go down 64, 32, all the way down to a single output, and that's our predicted score. So here we are compiling the model, and our loss function is mean squared error. I talked about this in another video. We take the square of the error to get rid of negatives so that we can get a good sense of how far off we are. Model.fit is going to run the actual training, and then we can do some predictions and calculate how good we did. And I also asked ChatGPT to write some code so that we create a plot where we compare what we predicted against the actual, so we can get a sense of how well we did in addition to just that numerical error value. Let's go ahead and run this code. And as it runs, you'll see the error loss, which gets better over time as we go through iterations. I've told it to do a max of 100 iterations, so it's continuing, and you can see the loss is going down. So this loss means that we're at a mean squared error of about 4 or 5. It's varying a little bit. We're not seeing as much improvement through these last iterations, so I think we've basically stabilized and we're going to do as good as we can do. All right, here is our actual versus predicted graph. So what we're doing is across the X index, or the X axis on the bottom, we're just plotting a dot for the predicted value and for the actual. So what you'd want to see here is very little blue, because that would mean that our predictions are right on top of or very close to the actual. So we're obviously not doing that perfectly. We're getting close. You can see that the scores are pretty concentrated in between 60 and 80%. There's also a few outlier blue dots that students who scored a 90, a couple even close to 100. So our model didn't do a great job of predicting those because those were outliers, but where we're kind of clustered in a normal distribution around the around 70%, a little less, we're doing a pretty decent job. Okay, our mean squared error is 4.5, which sounds like we're actually could be off by 4.5 points, but that is the square of the error. So you actually, to find out what the standard deviation of our error is, you would want to take the square root of that. So if we do that math real quick, our actual, or what we expect to be off, is only a couple of points, which is actually pretty good. So this means that 68% of the time, our prediction is going to be within 2.1 points of the actual score that the student gets. That's pretty good. So our neural network was able to take all of the features and come up with a pretty good model that predicts how well a student is going to do based on all of those factors. Okay, so now let's take a step back. We've seen a detailed neural network use case where we can take a bunch of input data and make a prediction. But the concept of neural network is finding patterns in the data. So how do we go from there to something like a generative AI, a tool like ChatGPT? This diagram here is a very simple representation of what a large language model looks like. It's got multiple networks inside of there, and you can see the first row here in our network is parsing the input. So when you ask ChatGPT a question, it's going to take that prompt, it's going to convert it into a text embedding. So again, neural networks only understand numbers. It's got to convert your words into a series of numbers. I'm going to talk about that in a separate video. It's also going to add, as part of that input, a positional encoding so that I know the order of each word in the sentence, because that will be important. The multi-head attention mechanism, those are networks that are trained on trying to figure out what are the important parts of your prompt that the model should pay attention to. And specifically, what tokens in the input relate to other tokens. So I've got an example prompt on the lower right. What is the capital of Florida? You can see this is a notional diagram. You can see the weights or the importance, or rather the attention I should pay to the different words. There's an increased attention on the words capital and Florida, and those of course relate to each other so that the model would be able to predict that the next output token there is, of course, the capital is Tallahassee. So that's a short introduction to why machine learning is so critical for AI. Hope you enjoyed this video, and I'll see you in the next one.